Andre has posted this tweet a while back. He says that with the many puzzle pieces dropping recently, we should consider LLMs not as a chatbot, but the kernel process of a new operating system. You know, it can orchestrate all of these things, and it can even act as all of these things. It can act as an operating system, it can orchestrate databases and so on. But I want to say, Andre, an operating system is nothing. Your creativity limits you thinking inside a box. What we're doing here, we go beyond and we implement an entire CPU in GPT. So I can run any program that I want. I have a compiler and I can run any program that I want through that compiler, and I can then execute it against any language model in the background. Let me show you how this works. I have a deal for you. You listen to me for 30 seconds to talk about today's sponsor, Weights and Biases, and by doing that, I'm happy, you're happy, Weights and Biases is happy, everyone's happy. If that sounds good to you, then here's the deal. The course Training and Fine-Tuning Large Language Models has been created by Weights and Biases and is completely free. This is a free course about, well, training and fine-tuning large language models. The lineup of instructors they have, as you can see right here, is sweet. Like, these are seriously good people, and you might recognize one or the other of the current machine learning landscape. The course is done together with Mosaic and contains 37 lessons. Now, I already said it's about training and fine-tuning large language models, but the column here in the middle is what I'm personally most excited about. Curate the dataset and establish an evaluation approach. From practice, and I happen to be more in industry, more in practice now, I can tell you that, yeah, fine-tuning is flashy and prompting is flashy, but to even be able to measure quality of something like a language model, especially one you've trained yourself, is among the most crucial and among the most demanded skills there are. Thanks to Weights and Biases for sponsoring this video, and let's go on. Hello everyone, look at this program right here. I'm gonna run it. It's called FizzBuzz, and it's often used in programming interviews. The idea is you iterate from a number from 0 to 30 in this case, and every time the number is divisible by 3, you output the word fizz. Every time it's divisible by 5, you output the word buzz, and every time you output it's divisible by both, you output the word FizzBuzz. Otherwise, you just output the number. And you can already see there is an output. We have an output, FizzBuzz. Now, 1 is the correct next output because that's not divisible by 3 or 5. And we hope the next output is going to be 2. Let's wait, and the excitement is palpable. 2, there it is. And the only thing I wish for now is a little bit of fizz for the next output. Fizz, there we go, that's it. Yo, so you may think, what's the matter? It's like the simplest C program ever, and I'm making a big deal about it. So, you know, what is it? Let me show you, let me clear this and turn on debug output. All right, so if I turn on debug output, a whole different picture appears. Look at that, it's going, it's doing, all of this is happening, and until you actually see a print output, there's gonna be a long time. So what you're seeing right here are FizzBuzz, there we go. What you're seeing right here are machine instructions getting executed against a processor. Usually, the way a computer works is that you have what's called code. And code is a set of instructions. It's loaded into memory, so there are instructions, and there is a program counter that just kind of runs through these instructions. And every code does something. So you have the central thing, the CPU, and the CPU takes a piece of code, and it's supposed to do computations. So it has these things called registers, let's call them buckets. So these are registers, and it has memory, and it has input output, and so on, all of this available. So the CPU gets an instruction, for example, move some number from register number 4 to register number 8. So what it will do is it'll take it out from register 4, and put it into register 8. It can also do something like, how about you compare? So that's a really interesting instruction. How about you compare CMP register 4 to the value 1? Okay, and you store the result in register 2. So it'll go to register 4, it compare it with the value 1, and it will store either a 0 or a 1 in register number 2, whatever that is. And then the next point, the next instruction here could be something like branch or conditional branch, depending on register 2. And if register 2 is true, then go to instruction number 4, otherwise go to instruction number 8. So we're here, we look at register number 2, and if that is true, right, if before this was register 4 was equal to 1, we're going to jump to one instruction, otherwise we're going to jump to another instruction. This is how at the lowest level your computer implements things like if conditions. You can do math here, you can sum two things together, you can jump around, control flow, loops, and so on. All of this is implemented at the lowest level by instructions to the CPU. Now, okay, what does this have anything to do with this? And why is this video called I built the most expensive CPU ever? You might already guess what's coming right now. In fact, all of the instructions that you see right here, they are in fact CPU instructions, and each one of them is getting executed not by the actual CPU in your system, but by GPT simulating a CPU. So I can run any program that I want. I have a compiler and I can run any program that I want through that compiler, and I can then execute it against against any language model in the background. Let me show you how this works. And this really is the most expensive CPU ever. It takes hundreds of instructions just to get to the first FizzBuzz, and every time an instruction is executed, I send a whole bunch of stuff to GPT and I get an answer back, and that's one machine instruction. We've come full circle. We've built CPUs, we have trained huge language models on them, and now these language models can act as CPUs. So fundamentally, when you write computer code, you at some point need to make it into machine instructions, which means you need to compile it in some way. Now, granted, languages like Python and JavaScript, they do a different thing. But if you write a C program like this, something has to take it and compile it. And that's usually a compiler. Now, what the compiler does, the parts you may know, is it's going to turn it into assembly code. So GCC can do this for you. And if you look at the generated assembly code, you can see much more of what's going on. This here is FizzBuzz compiled for an x86 architecture. And you can see all the little operations right here. We first push some stuff, we add some stuff, we push some stuff, we move some stuff, and eventually we'll compare some stuff and we'll jump around depending on the results of those comparisons. We multiply things here, which certainly has something to do with the fact that we're computing remainders of multiplications and so on, of divisions. And all of this you might be familiar with. Now, if you're using something like macOS, like I'm using right here, the actual compiler you may use isn't necessarily GCC, but a compiler called CLang. I'm not exactly sure how it does it. Now, that has a LLVM toolchain in the background, and that essentially means LLVM is a toolchain for many, many compilers, not only C, but C++, any kind of language can implement an LLVM pre-compiler, let's say, to turn its program into LLVM instruction. And then LLVM can take care of really outputting the assembly or the machine code for a given architecture. So LLVM is this unified thing. And if we look at that, it's actually much more readable. So here is the LLVM output, the LLVM intermediate representation for FizzBuzz. And this looks like something one can actually understand. Assembly still has a lot of high registers, low registers, and blah, blah, blah. I don't want to deal with any of that, but this here, this seems doable. So what do we need to do in order to achieve our goal of building a GPT CPU? First of all, we need to parse this program, and I've done that. So if you look in the parsing file, I've written a parser to parse all of the relevant instructions right here. You can see signed remainder, addition, you can see right here store, branch to labels, and so on. So I've written a parser that takes LLVM intermediate representation and builds essentially an abstract representation of that I can then use to continue. The next thing I did is I built a reference implementation of a CPU. That means I have built something that in just pure Python code emulates the CPU. So you can see right here, I have constants, which are usually defined at the beginning of the program. I have registers and I have memory. And these, I'm kind of cheating a little bit right here. See, usually things are way more complicated than I'm doing this right now, but whenever possible, I'm just kind of storing values in the registers and not pointers to them, and then I have to trick around a bit when it comes to arrays and things like this. In any case, I'm emulating a CPU right here with Python, and the idea is just that I need to make sure that my whole parsing setup works. And so you can see right here, I am going through the operations and I'm kind of implementing them with Python. Addition, easy. Multiplication, that's that. Array lookup, certainly. And all of these types of things are just implemented in terms of pure Python code. We can actually run this right now. So if I actually go back here and I use the reference implementation, you can see FizzBuzz in all its glory. And I hope that's correct at least. It probably is. It probably is. So this gives me confidence that my whole parsing and so on is correct. And it obviously runs way faster because I'm just kind of emulating a CPU in Python. However, what I did next will shock you. So next I implemented a VM based on GPT. Now in this VM, I'm still managing the registers myself. So the registers are just going to be a dict that I manage. However, now every single operation in here is a prompt. For example, if I need to get something from registers, what I'll do is I'll send the prompt, look at the registers, and then I'll send the full registers and I'll say, now get me the value of a certain index in the register. It's up to GPT to look up the correct thing in that dict and give it back to me. I have addition prompts, I have remainder prompts, I have comparison prompts, as you can see right here, even system prompts. You're a very keen observer. All right, let's dive into this. Let's look at this block right here, with the label number 6. So the first thing it does is it actually loads from the pointer number 2 in the registers into a value into number 7, so into register 7. These are abstract registers for now, but bear with me. We can see right here that in the debug log, this is from the program code what we need to do. This is my parsing of this line. Now I sent this to GPT. I say, look at these registers right here. So I have registers, number 1 is 0, number 2 is 0, and so on. These are registers that I manage, but I just sent them to GPT as a string and tell it, get me the value of number 2. So this corresponds to this line right here in the code. And the system correctly says that's 0. Okay, so the next thing is we need to assign this to the register 0. All right, assigning in this VM is simply me putting it into the registers. However, in a later iteration, which I'll show you later, even that is done by GPT. So the next thing is we want to compute the remainder of the register number 7, where we just stored something, with the number 3. All right, so the first thing we need to do is we need to read from the registers. So I'm again going to send the registers to GPT and say, get me the value of register number 7. It says that's 0. That is correct. That is indeed 0, as you can see right here. Then I let it compute the remainder. So get the remainder value of 0 divided by 3. Again, it says 0. That's correct. Assign that to number 8. That's up here in the code. And then we'll compare. The next instruction is a comparison, an integer comparison between 8 and 0. Again, we look at the registers, we get the value of number 8. It says correctly, that's 0. And we execute the comparison operation. Are 0 and 0 equal? You're a very keen observer. And we get the answer yes. So let's assign that to register number 9. Note we can't control what GPT says. It could be like, yes, that's true, or anything like this. Whatever it says, we'll just store it into the register. Now further down, we're going to do a conditional jump. So look at the registers, get me the value of number 9. And I have a bit of a truthiness conversion right here to be a bit robust. And I do a branching jump right here. But you can see that for given instruction right here, there's either going to be one or even multiple GPT instructions that go along with it. And thereby, this is truly the world's most expensive and most faulty, probably, CPU. So let me show you a bit of a different program right here. And it's called Snek. And if I execute this on this, you can see it's a very basic form of Snek. So I can move the little O around until it kind of eats the star. You can see it works. And if I eat it, I actually win. It's not a complicated program, but it's quite a bit more complicated than the FizzBuzz program, as you can see right here. But I didn't just implement FizzBuzz, right? We have a fully fledged compiler from any C program to running it on GPT, and that's exciting. So all we need to do, modulo sum ops I haven't implemented. All we need to do is we need to run this through LLVM, get the intermediate representation, and then run it through my parser, and then we can fully play Snek on GPT. And how awesome is that? Who before has played Snek on GPT? I know the next iteration is Doom, but so if I run this now, this is gonna go and go and go. You can see how the registers get slowly filled up with values coming back from GPT, and we're doing comparisons, we're doing all kinds of math, we're doing additions and remainders, and you can see it kind of screwing up. The answer is 1 is here in the registers instead of just the number 1, and that will flow into next prompts and so on. So this is an extremely faulty system. It's extremely inefficient. It's extremely wasteful. Like, we're using the world's most powerful language models, but we're doing it in service of playing Snek. And I think if anything, that's a cause that's worth it. In fact, it's going to take about 600 instructions until I can do the first input in this program, conditioned on it never failing, because it will just randomly decide that now the number 2 is actually greater than the number 30. And oh, look here, it made an array. That's certainly good. I'm pretty sure that's good. Yeah, so you'll see. It has a few faults and it has a few sharp corners, but in general, it kind of works. And not only that, but I've gone further than this. See, not only have I made a basic VM that just executes the instructions, I have also made one that even manages the registers itself. So instead of the registers being a dict, the registers are now just a string that I initialize with an empty dict, but it has to do all of this stuff by itself. And as an extension of that, I've implemented this beauty right here. So I call it Chad GPT VM, and the prompt is kind of always the same. It's, look, bro, I know you love to talk, but I really just need the answer. Please don't explain. You have to. I'm really not good at prompting. But get from registers is implemented like this. Bro, look at these rad registers. Bro, for real, just tell me the value of register something. Addition is implemented as, yo, what's the sum of this and that? Bro, for real, do you know how remainders and stuff works? I really need the remainder value of that. My man, you're mad good at multiplication. And it's a beauty to watch this work. So let's do that. I literally can't wait anymore. All right, this is now considerably slower because not only am I asking it for, any particular register value, but I always send the full state of the registers and I get back the full state of the registers. Now, nothing constrains it to make a dict and send me back a dict. It could send me back whatever it wants. Sometimes actually it does that. Sometimes it just kind of sends back something else. It just puts some text around it, or gives me some friendly comments. So you see, my main man, I need you to store the value 0 in register 9, and these are the current registers, and it gives me the result. Again, has 9 here, but also 9 here. So it just kind of doubled up the registers right here. And yeah, that's certainly not good. So I guess register 2 here kind of holds another dict with the registers that's kind of closed here. So, like this CPU, it might need some work. Watch out, TSMC. We're coming for you. You will not be able to compete right here. Nvidia stock goes, this is not financial advice. Nvidia stock, boom. TSMC stock, boom. Chad GPT stock through the roof. This just shows if you set yourself a goal, you can achieve anything you want. With that being said, the code here is on GitHub. Do with it whatever you want. It's a giant waste of money and time, but you can play Snek, and what else is there? That was it from me. Thank you very much. I'll see you around. Bye bye.